I'm gonna be waiting. Yes, we are live and we are just 3 minutes late. Fantastic. I That is my mistake because I have all those lectures back to back, and I should have at least incorporated 5 minute break. So everyone who's joining us, please be patient. We're gonna be there. Everybody knows where to go, but sometimes I need to send the link again. So
Yeah, it's
Leander,
the yeah,
thank you so much for joining me. We already recorded one thing yesterday,
yes.
but and today we're going to be talking about the computer vision tasks that go into the image analysis of pathology images.
Yeah,
So before we dive into this, let's talk about you. Who are you,
sure.
Leander? Tell us
Yeah,
a little bit about yourself.
sure. My name is Leander van Eekelen. Pleased to be here. I am a PhD student in the Computational Pathology Research Group at the Radboud University Medical Center. The speakers just before me are my colleagues. Um, I have a very, I think, straightforward career path. I did a bachelor and a master in biomedical engineering. I did one course in medical image analysis, and I thought, oh, this is great. I really want to do something with this. And then did my bachelor project, my master thesis, and my master internship. So all of those courseworks I did on computational pathology. And it also happens to be the case that I did all of those projects in the same group as where I'm working now. So I liked it a
It
lot
seems to be a good
there.
group because there are a
Yeah,
couple of people who stayed like for a long time and didn't want to go anywhere else.
indeed,
So
it's a very lovely group. So I yeah, did all of my coursework there. I graduated and then I started doing a PhD in this group, where I now work on immunohistochemistry quantification, specifically for program dev ligand 1.
mm-hmm.
So that's
Okay.
basically the whole story.
Okay, so let's dive. I'm looking at how much time we have. We have a full hour for this. Fantastic. So let me welcome our guests, meaning you're my guest, but we have also guests from the audience, and they are live with us on different platforms, LinkedIn, YouTube, and Facebook. So drop a hello in the comments and let me know where you're tuning in from. Where in the world are you tuning in from? I'm in Pennsylvania, Fairfield, Pennsylvania. Leander, where are you right now?
I'm currently in Eindhoven, which is a big city in the south of the Netherlands. I'm basically, I think, 80 kilometers under the previous speakers. Those are in Nijmegen, where the Radboud University is located.
Mm-hmm. Okay, so fantastic. Let's talk about computer vision approaches. Let's
Yeah.
talk in general, like image analysis for pathology
Mhm.
images. What do we do there? How do we do it?
Yeah, I think this is a very broad topic, and I will be very wary of not going in too much detail that we will cover at later lectures during this
Mm-hmm.
series,
Yeah,
because
let's give an overview.
for example, I can dive really deep into deep learning, but I think we have a lecture right
We have,
afterwards that
yes.
covers deep learning, so it's a little bit of a precarious balancing act, but we'll try. Where do we want to get started, Alexander? Like, do you have a warming
Let's
up
start.
question, or?
Yeah, so let's do like computer vision. Let's maybe talk about the differences between us seeing things like immediately and knowing everything, and the computer seeing things.
Okay,
What's the difference between there?
sure. The funny thing is, you say that what's the difference between us, like something seeing immediately, but of course there's a very complex biological process that goes into like light entering our eyes, and then like it's not magic that makes us suddenly realize, ooh, there's like an object in front of us. It's a really complicated biological process that I'm definitely not qualified to talk about in depth. But in general, there's quite a bit of processing that goes on already in the pathway from your eyes into your brain. I think there's some funny, um, almost like overlaps or parallels that we can I can draw back to when we get further along in this story. But basically, light enters our eyes, travels via a nerve to our brain, and gets processed there via a very, very complex biological process, as compared to what a computer vision system does, which has to interpret pixels. So we look at wavelengths. We basically have a light enter our eyes, but then a machine, and let me think about this for a second. It just receives on the most fundamental level, it just receives pixels, and then it has to do something with that in an intelligent way, and then we basically decide what the logic is behind the interpretation of those pixels, because fundamentally it's just an array of values in, and then there's some process that we decide on that turns image into sensible output.
And how do you this is okay? So this is for when we try to interpret image with a computer algorithm, right? So what are those different things that you can do in an image?
Sure.
And we talked a little bit in the lecture that we're going to have later, but I want to focus on this. So the most common things that you can do, you can segment an image, you can classify an image. There are different types of segmentation. Let's talk about that and how it is done.
Sure. So there's basically different kinds of, I always think of them as tasks. There's different kinds of tasks that you can perform on an image depending on what you're interested in. So let's say, let's keep it pathology related.
Let's keep it.
We might want to discriminate where cells are. So we are interested in in this like array of pixels, where are some dendrites, or where are some lymphocytes? Doesn't really matter. That's what we would call a object detection task. There, the goal is I want to predict the coordinates and then sometimes, not necessarily, the spatial extent of an object. So I have an object represented by fist that's somewhere located in an array, and I need to predict a XY location, and then sometimes also a box that surrounds that object.
So I can have a visual for us, because sorry, not this visual. I need to share my screen. So 1 second. Yeah, so I have this visual, which we have from Path Presenter, and our Path Presenter is nice enough and fantastic enough to let us use those images. Those images are there for free, and we can use them. So whenever you need a pathology image for me to pull out, let me know. But basically, okay, we're talking about cells, or are we talking cells or nuclei?
Well, it depends on what kind of object you, of course, want to detect, but let's stick to nuclei for right now. So basically, every object here, I need to predict an XY location for where it is, and then have a bounding box surrounding it.
That's my version of the bounding box. If somebody was asking.
So that's object detection.
So here I want to talk a little bit about this bounding box. So we want to detect them, and you obviously see that I try to make a square. It means it's not it's just showing me where it is and those coordinates. It's not exactly the boundary. So let's structure it that way. We're going to be talking about the different tasks. Like now we're talking object detection. I will try to do some drawings for you, and based on what you're explaining. So if you're explaining well, I should do good drawings. And then let's talk immediately about applications that come to your mind and that come to my mind, where we want to use this instead in contrast to other approaches. So
So there's basically always a reasoned or an intelligent there's always a reason behind why you pick a certain task. So for example, in my daily work, I want to be able to detect PD-L1 positive tumor cells. So that's an object detection task. I don't think you have a PD-L1 immunohistochemistry slide on hand. Doesn't really matter. It's not that important. But basically, I want to be able.
I might look for it.
Okay, go ahead. I'm interested in specifically the number of cells and where they are spatially related to each other. So I can solve that task by just doing object detection. And I think at this point it's good to contrast it with some other tasks. For example, why might I not do something called segmentation?
Yes. So let me clear my annotation here. And no, I don't have a PD-L1, sorry.
Yeah,
let's find a nice nucleus. Yeah, here these guys are nice.
Yeah. So with segmentation in general, we are, instead of doing a XY prediction of where something is, we are actually trying to describe pixel-wise where an object is and what its spatial extent is. So
spatial extent is the keyword.
Yeah. So basically, what shape is it actually, and where is the complete object? So if you were to think again in terms of pixels, you have to, ideally, this doesn't always happen, of course, but ideally you have a method that's capable of, per pixel, saying this pixel belongs to this object, and this pixel belongs to that object, and this pixel belongs to this object, blah, blah, blah. Then there's a few different flavors of segmentation that are also important to note. I was just talking about segmentation in general, but there's subtypes.
So here's my version of segmentation, and here, see, I didn't segment this one well. But yeah, so basically I wanted to incorporate the whole thing in my annotation. So let's say these are segmented.
Exactly. Yeah. And so then a couple of flavors. The most kind of, I think, intuitive is something that we call semantic segmentation.
Yes, let's talk about that.
I think maybe a very quick step back. In a segmentation task, or in any computer vision task in general, we are interested in certain objects of interest, or maybe I can also use the term labels. We, in detection tasks or segmentation tasks, we might be interested in, I want cell type A, cell type B, and cell type C. And then my segmentation algorithm produces a map or a array with each pixel being labeled as either cell type A, cell type B, or cell type C. That's specifically semantic segmentation. So and the clue,
So if I wanted to do semantic segmentation, I would have to annotate every freaking pixel of this thing.
Exactly. The main clue, or the main the takeaway from semantic segmentation is that you do not differentiate between discrete objects. You just segment. This pixel is cell type A, regardless of what specific cell it might belong to. So here we get into kind of a distinction between, you can segment stuff or you can segment things. Things are countable.
Yes.
Yeah, so things represent discrete objects. So that might be cells, or that might be nuclei, or that might be glands, or that might be fat cells. I don't know.
So let me just here, like a vessel here is going to be a thing, right?
Yeah, that's a thing. But then you also have stuff, and these are very informal words, by the way. An example of
Shall we not use them in papers? Are you saying that we should not use this terminology in the papers?
The funny thing is, I just finished reading a paper about separating stuff from things.
That's it's totally official terminology.
Yeah, that's kind of a famous computer vision paper. But a good example of stuff would be the background around this particular
Like
section.
this here.
So if you zoom all the way out to like
Okay.
1x, then a good example of stuff would be the background of this. Yeah, exactly. That's
Okay.
stuff, because we it's not a countable object. Basically, with semantic segmentation, you treat everything as being stuff. I don't make any distinction between like objects. I just say this pixel belongs to stuff cell type A or
So
cell type
if
B.
I had okay, because usually like when you want to do something with the nuclei, then you want to count them or do something like you want to have an object. And so semantic segmentation, you're telling me semantic segmentation is not for objects. Don't use it for objects, because if you do, you're gonna have something like that.
Yeah. So
This is
yeah, there's a small caveat, of course, and I think here it's also good to move to the next concept, which is instance segmentation, which
yes.
contrasts very nicely with semantic segmentation. So
let me
instance,
just
yeah,
insert one thing. So what you call stuff, I also sometimes call regions, because when you're going to have a region of nuclei, and the area of this should be correct. But if you want to count them, then that's not what you want. So if
yeah,
you want both, the best of both worlds, object detection and segmentation, we can do what you started talking about. So let's
instance
talk about that.
segmentation. Yes. So in this case, instance, I think, is already kind of a intuitive word, or it kind of like helps you to understand the concept. Instance, as in it's a discrete object that you're segmenting. You have, if you build a instance segmentation model, you have decided that apparently it's I see value in also discriminating between discrete objects. So okay.
Are you
It's fine.
still?
It's fine.
Yeah.
Okay.
Yeah. You're back.
Let's see. So intersegmentation, I am still classifying objects into types.
And
So
you're using word classifying. We're gonna talk about classifying after we explain this one.
Yeah, exactly. Like it might have in a retrospect be easier to start with classification, but it's fine.
That's okay. Let's finish this one, and then we're gonna insert the classification.
So,
and if anybody has questions about these things,
please,
and drop this in the comments. I'm gonna be showing them. If anything is like not logical, we kind of know about this, so we probably might not be aware when we're like jumping around. It's for you. So if this is not structured correctly, you drop us a comment, and we're gonna go back and explain it the way you want it to be explained.
Yeah.
Okay.
Please.
So instance segmentation.
Yeah, so it's very straightforward. Instead of doing cell type A, cell type B, and then regardless of objects, you treat everything as stuff. Now everything becomes things. So everything is a discrete object. And that means that your model, instead of only outputting the segmentation, the actual like shape of the object, you then also start giving with as output, for example, number 1 for object 1 of cell type A, or cell type C object number 5. Yeah. So then every object belonging to that class gets a number. So this is object 10,000, and they're all discrete objects. This is very nice because if you have an application in which you are concerned or interested in the actual shape of discrete cells or individual cells, then you might choose instance segmentation, and it's a sensible way to go, basically. There is some trade-off, and now I think we're getting into some more nuanced deep learning stuff. There are trade-offs between choosing these types of model tasks. I don't know if we want to get into those
Yeah,
right now.
let's get into it because like when you think about it, okay, you have the bounding boxes, like okay, you have squares if you don't want to have the shape, if you just like want to count. So one application, we were supposed to talk about applications. One application is going to be Chi67 positive cells counting. Chi67 is a proliferation marker, and in many types of tumor, this is a sign of malignancy if you have this index above some certain way, a certain number, right? But you don't care how those nuclei are shaped. You have to count, I don't know, 500, I think. And once you have counted so many, it's good. The bounding box, dot, or whatever you want to drop in this nucleus is enough.
Exactly.
But then why should we then not just go for instance segmentation? Then you have everything. What's the deal? Like, why can't we just go for instance segmentation for everything and have everything always? What are the trade-offs? And I'm asking about that because we touched about it in the other lecture as well. Because then in the end, once we have explained all these, it comes down into, okay, what's your problem? What's your method? What's your pathology problem? What's your computer vision method? So now tell me, why not instance segmentation for everything always?
Yeah, sure. If you consider the actual process that goes into training these models, you always need data. And one issue with this is that, well, okay, we all know that collecting data for training these kinds of systems is very expensive. Expensive mostly time-wise. You're asking a medical expert to do a complicated yet repetitive task for you. The nice thing about, for example, object detection is that it's a lot simpler in terms of annotation or generating the labels for that task than, for example, semantic segmentation, because then you have to draw a line, and it goes even further for instance segmentation, where you have to, as a annotator, as the person who is making these labels, you then have to actively segment every object. So basically,
so let me do a quick demo. And this is, I have to click more than I should, but let's do object detection, right? Does it make a dot? I would just want a dot. You can start drawing. Okay, we could just make like a little line, right? And I just go and draw a line on each of them, and that is my object detection, right?
Yeah, exactly. You have you have basically clicked in the middle of the cells, and you have noted that there's an object right there.
So let me do semantic segmentation of the nuclear region. So let's say these are, is it drawing? I'm making some funniness here, but let's say I'm annotating a nuclear region.
Yeah, and basically you could almost already annotate the entire slide here, because they're all nuclei. Or if we make it a little bit more general, they're strictly not all nuclei. You're also including cytoplasm, so we could say they're all cells. And then it becomes a lot easier to annotate. This is a nice region of cells. We have just annotated them as these are all belonging to the same cell type. But then, of course, there's a lot of misery now, because now we want to do instance segmentation, and now instead of annotating these nice big regions, you're forced to segment every single nucleus. And here, yeah, exactly. And here the shape really matters, because if you're inconsistent, you're showing inconsistent data to your model.
And I just did show here inconsistent data. If you see that there is like lighter cytoplasmic, I should be more detailed than that. So I already did a sloppy job here.
Yeah, and there's been research done on how big the effect is on inconsistency between, so you let one reader do one cell, and then you let another reader do the same cell again. You train on both sets, and then you can see actual measurable variability between model performances based on who is drawing the circles. So that's a nice insight. It shows that the quality of segmenting cells actually really does matter.
Mm-hmm.
Yeah.
Okay. Yeah.
I think it's also worthwhile to jump all the way back to classification, because that's something that we neglected. We've gone very in depth now on
Question.
segmentation. Yep.
Do you have anything to? So I heard this concept, panoptic segmentation. Is this a
Yeah.
thing?
Yeah, that's definitely a thing. It's a
If
very,
I
it's a
heard it,
very,
it's a thing.
yeah.
Or is it an object? Is it
No,
stuff
it's
or is
a,
it object?
it's not it's not stuff. It's a thing. It's definitely
Okay.
a thing. Panoptic segmentation. It's a novel concept. I don't think it's fully landed in the community yet, because for example, I hadn't heard of it until I think half a year ago.
Mhm.
It basically tries to cover the gap between semantic segmentation and instance segmentation, because as I
Mhm.
just alluded to, semantic segmentation on the one hand tries to cover everything as stuff, that there are no discrete objects. In instance segmentation, you cover stuff as, well, stuff. Okay, everything is
You go into this
stuff.
stuff and you like make shape this
Yeah,
stuff into
and yeah,
little
sorry,
objects.
I'm being very inconsistent with my words here, because these are also just like regular day words.
Yeah, yeah.
What I meant to say is instance segmentation covers everything as things. So it's
Mm-hmm.
stuff and things.
Things.
And one problem with instance segmentation is that it's hard to make a model that also does background segmentation.
Yeah.
You want to segment all of the cells, but at the same time, you also want to segment the entire background. But within the kind of reference frame or the understanding frame of instance segmentation, something like stuff, as in the background, doesn't really make semantic sense.
Mm-hmm. And that
So
brings me back to again this comparison slash contrast, computer vision versus human vision. How do I perceive this image? I see everything at the same time, and like I know the white is white. I don't care about this. And whereas the computer has to like do it, like I didn't even know that this was the way you had to translate it for the computer. I used to
yeah,
like get really frustrated that one approach would not tackle all the other problems. And first of all, there were not all these approaches at the same time. So the semantic segmentation was before instance segmentation, and
yeah,
now we have the panoptic. So yeah,
yeah,
let's keep talking about panoptic
yeah.
before we go to
Just to Yeah,
classification.
exactly. Just to dive very briefly into it. So, like I said, panoptic segmentation, or at least what the authors of the paper that proposes this concept propose, is it's a bridge between instance and semantic segmentation. So instead of being able to only cover stuff or only being able to cover things, you're now able to cover both things and objects. So
Mm-hmm.
the model objective is, I need to classify each object. So I need to give every object a label. So this cell right here, that's a lymphocyte. This cell right here, that's a neoplastic cell. This object right here, that's a mitotic failure. I also need to then say this object, its spatial extent is something like this. But then at the same time, and this is I think the crucial difference, I also need to then segment uncountable stuff, i.e. background or lumen. I think lumen kind of, yeah. So this is the kind of the
That's a super cool discussion
yeah,
that I've had in.
exactly. This is the philosophy that you then kind of like get bogged down into, because of course stuff and things are very vague words. So yeah, at what point is stuff a thing, and at what point is a thing a
Yeah,
stuff?
because lumen
So
is actually stuff because this is background. But then if you want to measure the diameter, then you're measuring stuff, measuring a region as an object, and you want the measurements for the object.
exactly.
And quick quick shout out to our people who are on the line with us. Let's do this because we're gonna at some point we're gonna stop explaining and we're gonna dive into applications.
Yeah.
Right here in the comments, your pathology problems that you're making image analysis solutions for, or something that you would want to have an image analysis solution for. Write the pathology problem, the pathology scoring that you're dealing with, and we're gonna at the end try to show them and say, which of those approaches would we use? Which would be the best?
Sure.
So
Yeah,
I'm
that's a good
waiting for
idea.
those comments, and we are now going to be talking about classification. That we should have started with.
Yeah. So the reason why I said classification is something that we, in retrospect, should have started with is that it's kind of the simplest concept to get across. We dove straight into the deeps at the beginning. Classification is very simple. I have an array of pixels, and these pixels represent, for example, cells or some pathology image. I then want to give a label to this image that describes the entire object. So you might, and this can be basically everything. So the most sensible label for us would be, for example, contains cancer, yes or no. So this is a label that describes the entire content of the image, and I want to draw an analogy with semantic segmentation. Segmentation in general is you don't classify the entire image with one label, but instead you give a label to each pixel. And then if you visualize this, you get those nice maps that overlay images or the stuff that Alexandra drew on the cells in the pathology viewer. You would basically do classification or at a cell level, or no, at a pixel level. So that's basically the relation between classification and segmentation. Classification is, as a concept, very straightforward, just a label for an image. And then I guess logical next question is applications.
Yeah, no, another question. But so label for an image is the, like, let's say for natural images, cat image, dog image, boat image, whatever.
Sure.
Whenever you get those reCAPTCHA, click on the one where that has boats, and they show you half a boat. But when you have instance segmentation and you are saying type 1, type 2, type C of a cell, you have to classify them. So how do you reconcile that? So you do classification on classification. It's, I don't know how to put it in the best way, because then you segment the image and you also classify the segmented objects.
So
comment on that wherever you feel like commenting.
So I think the way that you can think about this is that the model has a different objective in those instances. So or in those examples. In the example of classification, it's really picture in and then label out. And then some underlying process in the model is saying, after a decision process, this is a cat, or this is cancer, or this is a positive tumor cell. Then a model that is capable of also saying, oh, this is the spatial extent of this object, that has a different underlying mechanism. Basically, I think this is a good way to think of it. Because a classification model spits out one value at the end, and this value is a probability of that particular picture belonging to a certain class. So if it's very high, then it's a very positive, very likely that this image belongs to this label, and that's a classification example. But then segmentation model spits out per pixel a probability value of that pixel belonging to that object. So it's really a underlying model difference that causes this change in behavior. You either classify the entire image or you can classify pixels within an array within the image.
Okay. So for those who are on the line, drop us comments. Drop us also comments. Which of those tasks that we are describing are you using at the moment? And we have a comment from Brander. The tools you described that already exist just need joining into a single tool, like automated skin, non-melanoma, tumor reporting would be possible with the tools you describe. So that's like a bit of a... So we're talking about methods, then the methods in computer vision have to be translated into tools, because obviously, Leander, the tools that you're using is just, you probably coded in something. This is not a tool I can use. I can click and when I have a user interface. So that would be a tool that is for pathologists. And then next level is to incorporate it into the workflow, that it's not just the working with the image, but working with reports, working with the whole like how a pathologist works or how a scientist works. Yeah. So the follow-up comment is that the data sets do not exist yet. Yeah, there are some data sets, because you are using the Chameleon data sets for a lot of stuff, which just for those who don't know, Chameleon was a challenge, image analysis challenge. And those image analysis people in the medical community, they organized challenges to check which algorithm is best for a certain pathology problem. And the pathology problem for the Chameleon was detecting metastasis in lymph nodes, detecting metastasis of cancer, breast cancer, I think it was, in lymph nodes. So then you design an algorithm and everybody is competing. They have the same data set, which is not really common, like something that is kind of logical that you should have, and you benchmark everything against the same data set, but you don't, because like Brander says, there are no data sets. There are some, and you can, for all those changes, I think, Leander, correct me if I'm wrong, you can access those data sets, right? You can just get them. That's what they're from.
That's the whole idea of a challenge, that you basically make data available for users to build algorithms on, and then to submit results to a central location. That's usually the organizer of the challenge, and that organizer.
So you guys were the organizer of Chameleon, right? Or co-organizer?
Correct. Yeah.
Where are those data? Where are those images?
Sure. That's a very understandable question. So most of the time, I think we store pathology data for challenges on a platform called Zenodo. That's a platform for the storage of open source data sets. We definitely make those data sets available. If you ever want to see if data is available of a challenge, I highly recommend just going to the page of the relevant challenge, and there's a very high likelihood that there's a direct link to a Nodo or some other repository.
We're going to link later. I'm going to find the link to your images, and I'm going to link them in this lecture.
There's videos available.
You say open source or openly available images and data sets. The set of these lectures is openly available to everyone. I want to emphasize one more time that those lectures, they're going to be on YouTube. So, if you ever lose track of them, just subscribe to YouTube, and they're always going to be in this playlist. The playlist is Bridging the Gap. And maybe we're going to do it once again, so I should add the date. But we're going to also upload it to an open source repository for open source content. Once I know where exactly that is, I Googled it once, I'm going to drop the link. But let's move to applications then.
Sure.
Oh, and here we have our fantastic audience telling us where the Chameleon dataset is. Fantastic. Thanks so much, Kieran. I'm going to later copy it into the notes as well.
Great. Okay. So applications. Sure. So, for example, in my own personal work, that's a nice thing to explain, I think.
I work on... I have questions to that.
Cool.
Video one.
Yeah, exactly. Basically, as some of the pathologists in the audience might know, you can read PD-L1 immunohistochemistry slides and then determine something called a tumor proportion score.
Yes.
I don't want to get too much into detail because this is a very broad. I can keep it very broad in the sense that you can basically derive metrics from the output of segmentation or detection or
I can
classification
comment on this
tasks.
one. So I can comment on the pathology side of this scoring because I
Sure.
actually, there are countless of scorings in pathology. PDL1 is one of them. So PD1, the PDL1 program death ligand, has been proven to be this ligand that can be targeted by drugs. And there are several and then if you have this ligand, if you can visualize it with IHC on your sample, it means you have it and you are more likely to have positive treatment result of a certain drug that addresses this. The thing is that there are several drugs that address this, and for each of those drugs you score this differently. So the tumor proportion score
Is one of them. Yeah.
one of them. And then you have different ones. Sometimes you include immune cells, sometimes you don't include immune cells, but basically you say how much of this tumor is PD-L1 positive.
Yeah.
So the question or the task that the pathologist is tasked with is what percentage of cells is positive in the tumor. So how I see it, and I'm super curious how you approach it. And I worked on this in maybe 2017 with a group, and we were trying to. And you said you were doing object detection for this, and we were doing object detections. I can link to this paper later as well. But then I was looking at those images, and I'm like, I'm not counting those cells. I'm looking at the area of this tumor, and I'm visually assessing how much of it is positive. Is it 10%? Is it 50%? And the granularity of my thresholds is also another type for a day-long discussion. But basically what we ended up doing, we ended up switching to classifying stuff, classifying regions. So let me know how you approach this for this tumor proportion score.
Yeah.
And why you decided to go for the approach you went for.
Sure. I think this is a very interesting discussion because here you really get into the nitty-gritty of I need to decide what kind of setup of my problem is like most suitable. Like how will I phrase this problem that I will then solve with a algorithm? There's lots of different options, and I think all of them are valid to a certain extent. It's just a matter of what do you want to do with it. So I read papers, and I think that includes the work that you have done, Alexandra, on we, instead of doing object detection, we do semantic segmentation. We will segment.
I think when I was working on it, there was not even semantic segmentation was not even a thing yet.
Oh, okay. Well, basically you do.
Well, maybe it was, but we didn't really. Maybe that didn't spread throughout the community.
Okay, but regardless, I think that you probably did something akin to segmentation. So
yeah, we did segment the tumor, and then no, I think we did negative versus positive areas of the tumor. So yeah, we did segmentation.
Yeah, that's
areas.
Definitely one way to phrase the problem, and then it's very easy. You just take the sum of positive tumor cells divided by total number of tumor cells. So this is simply a matter of
area,
area of positive tumor cells divided by area of total number of tumor cells. So that's positive plus negative. And then my approach, in contrast, is I'm interested in the actual discrete cells. So my developed system is responsible for per cell deciding where is it, what's the spatial extent of the location. So it predicts a bounding box around the object, and then it decides is this a positive tumor cell, a negative tumor cell, is this a immune cell, or is this a other cell? And I should specifically say, is it a positive immune cell? The reason I
so you have like layers of stuff of things that you're doing, stuff and things. Yeah.
Yeah.
A
Yeah.
layer of tasks that you have to like stack on top of each other to reproduce the scoring, because
Yeah.
you still are trying to reproduce the visual
Yeah.
pathology scoring,
Yeah,
right?
exactly. The idea is indeed that I'm only basically automating the tumor proportion score, because you can also imagine how it goes with object detection. It's again very easy. You just take the sum of total number of positive tumor cells divided by the number of positive tumor cells plus negative tumor cells, and then you have your
Mm-hmm,
tumor proportion score.
mm-hmm,
But the
mm-hmm.
nice thing about the way that you phrase the object detection problem is that you're also capable of, for example, replicating combined proportion score. And that's a small nuance in CPS, which is a different metric for program depth ligand 1. You also include positive immune cells. That's
Yes,
usually used in, for example, head, neck, and shoulder
that's
cancers.
a combined CPS, combined proportion score,
Yeah,
right?
exactly.
Mm-hmm.
And then because you detect positive immune cells, you are then also capable of reproducing the CPS score of a hypothetical lung cancer slide. Um,
I
and
love that we picked this subject because we already are getting a discussion that by area might not be a good approach depending on tumor cell
yeah,
size. Uh-huh.
exactly. You can
And drop the
always,
comments if you're like disagree with what we're saying. It just gives us ideas for new research.
yeah,
This is new, and my paper is old. Your is going to be newer. So
yeah.
and
Thank you for the
probably in
comment,
the no, I don't
Jochen.
know because my people, I don't know where they even publish it, but like maybe yours is going to be higher impact factor.
Maybe I hope, but
We'll see.
maybe.
Cite us though.
Yeah. By the way, thank you for the comment, Jochem. I
Not a
agree
problem.
with there is this underlying question of if you just purely do segmentation, do you do an accurate job of representing the total number of cells? You could maybe argue that as long as the segmentation regions are large enough, then
Mhm.
the variability in cells kind of average out, and then it's fine. But you don't know this, of course, until you empirically determine this. So this is still
I
a
am
open question.
wondering, like when they were designing those scores for the clinical trials and designing those cutoffs, like if anybody of you in the audience is the pathologist that did that, please contact me. I want to see, I want to know how you did that because I don't know, like in contrast to Chi 67, where you actually have to count 500 cells or whatever the number is for the MD pathologist, but there is a number of cells that you have to count, and you go and count it. And like Leslie just said in the previous lecture, people actually go and do it. No, she talked about mitosis. But anyway, there's really like counting, mitotic counting. For the PDL1, when I was scoring it and when I was looking at the guidelines, like there was no way for me to count all the cells. Like if I had to prove that I counted them, I would have to tell you the number. And then I would have to tell you the number of all the cells. I was just not doing this. So
Yeah,
um, that's why we went for the segmentation approach because I was like, okay, the score might be per cell, but I'm not doing this. How about
yeah,
we do what I do with the computer?
yeah.
So here,
So this is indeed kind of a philosophical discussion about how do
I love
you
how close this is to philosophy,
yeah,
everything.
it honestly is, because you have to wonder, okay, in what way? So I'm phrasing this clinical metric that I'm determining via histopathology, and I kind of have to wonder, okay, how will I accurately represent this kind of very abstract, like total PDL1 activity? I can
Mhm.
either do cell counting, but we at the same time acknowledge the fact that no reasonable pathologist in clinical practice will count 100,000 cells in a resection, or
Resection.
10,000 cells in a biopsy is even still quite a bit of work. So um, yeah, it's a very reasonable question, I think, to wonder if you do either segmentation for this quantification or object detection, will there be an actual appreciable difference in accuracy of tumor proportion score? Very good question, and honestly, I don't have the answer. Yeah, so that's kind of a nothing burger, but yeah, that's sadly the answer.
So you guys are doing the combined with immune cells.
Yeah, so our system, the way that we phrase it, it allows us to both measure tumor proportion score and combined proportion score. You also have something called immunoscore, which is an even different way of determining this threshold for some other kind of immune checkpoint inhibitor. I don't exactly know how that works, but I could imagine that it's also reproducible with segmentation or object
So
detection.
immunoscore, the immunoscore I know is for colon cancer, and you
Yeah.
define different populations of lymphocytes. The way it works, there is like a signature combination of two different populations of lymphocytes. I think it's CD3 to CD8. We can Google it. And guys, if you can Google which lymphocytes are for immunoscores, and let me know in the comments, that would be great. And we have a fantastic comment from Mike. Mike, thank you for joining us. Here's a suggestion: automate stereological object counting with AI. Yeah, that would be the holy grail if we had like the whole thing with stereology. But that's a good thing that you brought up the immunoscore. Immunoscore, you count lymphocytes of different populations, and I think the outcome is number or ratios of those two. What would you use for this?
So you want to determine the ratio of two different cell types, if I understand correctly.
Yes.
Okay. And is this system based on individual cells, or is it based on?
It's based on individual cells, on lymphocytes. You do immunohistochemistry, so you have brown versus non-brown. But actually, you're not really interested in the non-brown because you relate one population to another population. So you have to CD3, CD8. Rita, thank you so much for. I want to show this. Rita, thank you for looking this up for us. So yeah, CD3 to CD8, you determine the ratio of this, and that gives you a prognostic information for colon cancer. Yeah. How would you go about that?
If you want to, that's fine. For this, I would instinctively reach towards object detection because you are interested in discrete objects. Again, we can have this kind of philosophical discussion on if you do so imagine you do segmentation. Is the variability in cell area an actual factor that negatively influences the accuracy of your ratio? I haven't seen the data, so I couldn't make that decision. But you're
think
kind
they're
of like
more or less the same size, but I never even thought about it. My instinctive was object detection. You count them. You want the number, you count them, and that's it.
Yeah, if you want to avoid this entire discussion that I just posed, then you can simply go for object detection, because I'm interested in discrete objects that have that are somewhere, and I need to classify them into positive and negative. This is a very, I think, suitable object detection problem.
I'm gonna share an image here. It's not colon, it's breast cancer, invasive lobular cancer from past presenter. But the problem that we're looking at is pretty similar. Although I want some negative cells here that are from tumor cells. Okay, no, yeah. Anyway, but the problem is you have those positive cells, and for Ki-67, you just count them. You need object detection. You could maybe use instance segmentation if you're fancy and the cost and model training is not a problem for you.
Yeah, exactly.
To avoid like when you have overlapping things, instance segmentation is a little bit better with that. Although I don't know, but basically, okay. So this is a object detection / basically all object detection. If you use instance segmentation, except for like the cost of training and processing, that would be a counterpart, right? Like a more granular counterpart.
Yeah, sure. And I have one sort of wildcard suggestion that's also an option. You can almost always ask yourself the question, why not do this problem in a way that we call end to end? So end to end is a very interesting concept in the sense that I don't care about the detections of the cells. I don't care about where they are. I just want to go from image in to prediction out. So this is not necessarily classification. It can be. And classification is a type of end-to-end, but you might also have something called regression, in which you predict from an image in, you predict a value out. So that might be,
A score.
perfect
Perfect
example.
one scoring,
Tumor
right?
proportion score. Hey, you can also always wonder, okay, why don't I just do image in and then tumor proportion score out? And that's honestly a very valid way of doing it as well. It's also, I think, quite a bit easier because you have this advantage of, okay, I need labels for this system. How am I going to get these? Well, pathology reports exist. I just extract PDL1 tumor proportion score from this report, and then I have a slide level label to train this end-to-end system
You
on.
don't have to ask anybody for annotation. You don't have to ask them for like
Exactly.
additional scoring. And if you like scale it with enough data, then you see like where your variability is.
Exactly.
See,
And
that's
then
a cool one as well.
Yeah, and then in later talks, I think later today, we will go into more depth. I won't, but my colleagues will on okay, well, how do these end-to-end systems work? How do they scale? How do they actually, like, what's the model that actually does this?
Yeah, and if we don't
Applications?
address it, I have to make a note on this one.
Otherwise, very interesting.
To invite the additional speakers. And if anyone wants additional like follow-up topics, drop it in the comments because that's definitely food for thought for us. And I already have a good relationship, hopefully, with you guys, and I can like then ask you for a little bit more of your time to join me at different times. One thing before we go, because we're at the end of our broadcast, and then one thing before we go, I have heard questions if there's going to be attendance certificates for this. Yes, we can do attendance certificates. You're going to have your name, and if you need to show that you took part in this and have a description what it was, and submit it to someone who actually if you need it for anything, we can do it. Just send us a direct message on LinkedIn is going to be the best way, or let's do LinkedIn, or in the comments that you need a certificate. We're going to be going through the comments and making you those certificates so that you can show off that you took part of this as well. Leander, thank you so much for joining me. Thank you for this discussion. I love that you actually end up, you're a PDL1 researcher. That's like one of the few scores that I actually work with computer scientists on, and we tried to translate. So thank you so much, and you have a great day.
Yeah. See you later, guys. Thank you for watching.
Thank you. Bye-bye. And we're going to meet again at 9:30, which is now. Oh, no.